Right. So thank you for that, James. So this work is joint work together with some forensic geneticists that I've been working with for quite a while now, and they came to me and they wanted to look at these ancestry informative markers, and an ancestry informative marker is something that should tell you about the origin of a given DNA profile. And so I think the intention is that they want to use these aims, as they're called, as an investigative lead. So it should sort of give you an idea of maybe the phenotypic appearance of somebody, or at least sort of a geographical pointer to where the genotype that you're holding in your hand, where does that come from, sort of in a ancestry setting. And the people here, they have started to look into sequencing of STR profiles, and they have this battery of things where they have STRs as we used to, but now they're sequenced, and then they have also phenotypic markers that should tell you about the pigmentation and hair color and eye color, and then some of these other markers they have available are these aims.
What are STRs?
Sorry?
SGRs?
ST.
Oh,
sorry, T. Yeah.
Right.
Right, good. So there are many different sort of panels or sets for these aims, and in principle they're just SNP markers, so simply nucleotide polymorphisms, and the ones that I've been sort of forced to work with are what my collaborators refer to as Selden aims and then KIT aims. So they're described in these two publications, and one contains lots of SNPs and the other one is 55. And how they were chosen and why, and I don't know. It was just screening and a lot of populations, and then they did some validation in order of sort of getting good predictions of sort of big ethnic groups and ancestry groups. So in order to have this machinery working, we needed to have some frequencies from global, covering global populations. There's this, most of you might know it, it's called Alfred. It's a allele frequency database that is hosted by the people at Yale. And they have genotyped a lot of different and unlikely populations around the world. So the prominent feature is that the sample sizes, they range from 6 individuals and then up to 144. So you have a pronounced uncertainty in these allele frequencies that you obtain. Another thing that is just sort of that's one of the things that I just accepted until now, at least, is that all these markers, they're independent. So we could just use the product rule Martin just described, and then multiply the things together. But some of these markers would be sort of in linkage with each other, and the linkage might be different for different populations. So this is one thing that we want to look at, but at the moment, most of these populations, we only have the allele frequencies, so we cannot do any assessment of this problem. But if people they sort of have the entire frequency, the entire genotypes available, then you can start looking into some structure. And we have genotyped some populations, but not overwhelmingly many. So when my collaborators they started to look at this, there were this software called FrogKB. So it's a knowledge database tool where you use the genotypes from Alfred in order to calculate the probability of seeing a given AIM profile at any population in that database. So you basically manually type in all these different settings. So you have for each allele or for each marker you type in what is the allelic configuration, AA or AG or whatever, and then it goes away and use the product rule, and then it gives you this list. So for this particular example, the most likely at least if you measured in terms of probability of the genotype in the population, would be these Druze population, and then you get sort of a picture showing you the different log of the different genotype probabilities. And then you can use this, so they highlight some that is in a magnitude less than the most probable one, and then maybe they should be of interest. So another alternative is provided by the live technologies. So that's when my collaborators, they go away and they do the analysis. Then this software from live technologies, they give them this output, a sort of a heat map on a map where you get dots of where it's sort of probable of observing this specific genotype. And because we are in Denmark, the Danish kingdom also represents or contains Greenland. So we are specifically interested in Greenlanders. And if you come up with a Greenlander and then you use the Selden SNPs for those reference databases that we have, then it's somewhere in Asia, which is not completely off in sort of when you look at how people have sort of traveled around the world. But if you go to the Kankit ones, then you're other places in the world. So we wanted to do something that we could control somewhat better. Another thing that we wanted to make sure of was that this uncertainty in the allele estimated allele frequency should be taken into account. You know, having only 6 observations from a sample should really sort of not provide much insight, I think. But the Chakraborty approximation, an old piece of work, they have sort of derived what we needed for this. So their assumption is that you don't have any dependence among the alleles, and you also have independence between the markers. So that's applicable in our case, at least until we have found a more clever way to compute the genotype frequencies for a given population. Of course, fixated markers would appear quite often because they're you select these markers to be sort of distinctly distributed in the different populations. So for some populations you would find that it's fixated, so you have either depending on what allele you're talking about, either 0 observed or all of them are observed, that being type A, say. So we made this small correction, making sure that we don't have any 1s and 0s in the frequency database, and I'm sure that you can make more sensible adjustments, but this one was just to get moving. So details are in the paper, and some of the work that was referred to here. Just James, he's the chair of the session, so James, he did something, and then he threw away all these terms, having n to some power, and that's a fair solution when you have a lot of observations from each database, say 100. But here, 6 squared is not a big number. We're making this number vanishing, so we have to take this into account, and we did that, and then we wanted to compute things on log scale, and then using the delta method, all these things are delivered to you. So this would be a Greenlander where we have ranged the genotype frequencies for each population and then ranked them from left to right, and then the width of the confidence interval is both reflected in the number of observations from each population, and also the actual frequencies that you observe there. So this would, I think, take some time for at least some of my collaborators to accept that is actually a lot of uncertainty attached to all of these estimates, these point estimates. So if you just go with these point estimates, as you saw from the frog KB, then you actually are neglecting that you have a lot of uncertainty here. So,
can I just clarify? So with one Greenland profile, and you've calculated its probability in all those different populations.
Yes.
Is Greenland in one of those populations? We can't read.
It's the top one, sorry.
Top one.
It's the top one, yeah.
And the next one is Mongolia. So
Yeah.
Yes.
And then some Japanese and
Yeah. Okay.
Yes.
Excellent.
and then
Red means.
red means
There's some.
yeah. So the red will be explained in 2 slides. So we wanted to compare the ratio of observing this genotype in one population versus another one. And then, as Norman he wrote on his blog this morning, you don't have sort of exhaustive things. You just have sort of exclusive things. So there are many likelihood ratios that you can compute. But we also just wanted to take into the variability into account, and then because we assume independence wherever we go, we just say, well, the variance of the log likelihood ratio is just can be at least conservatively approximated by just the sum of these two terms. So we don't want to exclude too many populations. We want to be conservative, so we want to have a long list of possible populations where this genotype can originate from. And this is where the color comes in. So we have the intervals, and then whenever there's a intersection between the topmost, that lower level confidence level limit, and then the upper from one of the other populations, we colored red, so we say that it's probable, and this is a 95% interval. So you can sort of stretch that if you prefer to have a bigger confidence interval. And then one of the things that my collaborators they said, well, going back to these Greenlanders, so we would like to have an idea of when is something big and when is it just something random. So you can always compare two unlikely events, and then you can say that one is 100 times more likely than the other, which is not really what you want. You want to have some sort of a good gut feeling when you report this. So we try to, and this is still work in progress, so I've changed these next two slides a couple of times because I'm still trying to make my head around this. But anyway, this is a idea that we say that we can form a log likelihood ratio where we say that the individual come from population J, and then that it don't. So the numerator here is simply just where we have a huge sample size of one individual. So xi here can either be 0, 1, or 2, and then we evaluate this log likelihood ratio, and then we can re-express this somewhat, and then when we under the
what are the P's, where do they come from?
They come from each population. So
Are they estimates?
They're
estimates.
They're estimates from so all of these different populations that I have.
Okay, so on the top it's got with the subpopulation estimates, and the bottom's got the global population estimates.
So this is a profile specific one where I only look at the frequency that I would see for this particular individual. So this is population J, and this is not population J. And then I want to evaluate the mean under the null hypothesis, meaning that the mean when population J is the correct one. So I take the score, or I form this score where I take the log likelihood ratio, subtract the mean, the expected value, and then divide by the standard error. And then this actually shows to be somewhat good, approximated by a standard normal distribution. I'll have some pictures, and we can also account for the uncertainties in the estimates for each population by making a similar approximation as the Chakraborty one, where we have terms that depends on the sample size from each population. And then this might not be the most sensible thing, but this is just a start at least. So we want to have can we say something about, is there a relevant population? I have this long list of 125 different populations. Is there any one of those that are particular of interest or relevant for my specific genotype that I hold in my hand? And one way of doing this is simply just evaluating the score for each of, looking it up in a standard normal distribution, and if we get a sort of sensible probability out of that, then we're okay in terms of trying to form likelihood ratio for each of these different pairs. But if it's too low, then we will stop and say, well, we don't have a representative population in the database, and then we cannot do anything more with that genotype in terms of aims. So here I have just simulated a profile where there is these the scores on the x-axis, so that's this standardized thing here, and then you have the genotype frequencies that we just have for each population. And you see there is some correlation between these two, as you would expect. And the greater the score, the better. And this is just a QQ plot of these things. So under the null hypothesis, it should be standard normal, which they seem to be. At least other simulations show that as well. So.
Wait, can
Yeah.
Can you go back to look at the lower tail?
Yeah, so this is when it's highly unlikely. So this is the populations that are very far away from the. So when you go to this picture, those are these populations that's far away. But this is still a work in progress, and I have to sort of make sure that things are correct before I'll start publishing things. Some of the things that we also did was trying to see how useful is this when you try to make some simulations. So here I simulated 1,000 different profiles, and then I looked at this maximal score. So it's not always the true population that is the maximal. And then I wanted to see what happens if I remove the true population from the database. And then because of a lot of these populations that I have in my database, they're very closely related. Some of them are Russian 1, Russian 2, so they're quite closely related, so it's just an arbitrary split. So there is not much to come for here, but if we go to the Greenlanders, then we start to see something, and that's at least indication of that there is something to go by here, but we have to do more research. And the thing that I sort of ended up doing when these collaborators, they came to me, they wanted to have a platform that they could use to do some analysis. So I made a interactive framework where the researchers, they can take their profile, they can upload it to a system, and then hopefully they would have some graphical aid that should. So now I'm offline. Otherwise, there would be a map here. They should be able to, for each of these genotypes, get a plot like the one you have on the left, and then they should also have the assessment of whether there is a probable genotype in the probable reference population in the database. And then by going away, so imagine there's a map here, right? So this map is there. Yeah. Then you can sort of zoom in, and you can click at the various populations, and then you get some information, and depending on what you click, you will start forming sort of a table of different likelihood ratios that you compare to each other, and at least this is sort of a way that we can control what type of informations are delivered to the forensic geneticist that should work on this. This is just a way of populating some R scripts that should be helpful, but without having the user to know to use R. So this is this shiny interface that is made available by RStudio. And I can highly recommend to use this if you have collaborators that are sort of scared of R, but you would like as a developer to hold the control and development in R. So I think that with some future work directions, so we would like to genotype some more populations. At the moment we have genotyped, I think, 6 or 7 populations and about 100 individuals from each, and then maybe use these genotypes in order to make a refinement of the dependency between the markers. We have also had some of the genotypes being analyzed in a dilution series. So what effect would an apparent homozygosity have on the probability of some genotype originating from a different population, and then hopefully make this this interactive platform more reliable and roll it out to the production framework in the forensic department. And yeah, that's about it. Thank you.
So it seems to me that you have a kind of a complicated way to decide if a population is plausible for a genotype by computing these scores in a way. Why don't you just look at the random match probability? If you compare the random match probability in this population to the distribution of random match probabilities that you get from the allele frequencies, then you can find which quantile of the random match probability distribution your profile is at. And if it's at the far end, say it's maybe the rarest or most common profile in this population, then I would say it's unlikely that its profile comes from that population.
Yeah, so it's basically, if you did simulations and then you would end up getting things that would look similar to this sort of more theoretical derivation of this score statistic. But the score statistic has a distribution, so you can also use it to say something about, well, that was the intention, that was to say, is there a relevant population at all in the database?
You can do the same thing by just looking at the RMP, I would suggest.
Possibly. But this is fun.
The delta method is useful for large samples.
Yep.
Justified on a large sample. Some of your population sizes where n is 6 and 20. How good is that going to be?
Well, it's so it, for instance, here in this so this is the Shakaborty one, right? And I don't know. I haven't thought about that actually.
But this is not the usual delta method. I mean, it's a higher order.
Yes, he's taken an extra couple of terms.
Yeah.
But it's still an expansion around the estimate.
Yeah. I'll have to write that down. Yeah. Thank you.
I suggest we thank all three speakers again for an excellent session.